So let's learn more about the independence set. In order to deal with the independence set in a graph, we define independence polynomial. In G, we consider all independent set and we add the monomial with the exponent, which is the size of independent set. This be the independence polynomial of G, or it's also called the partition function of G. And we consider the following distribution over the independent set of G. The hardcore model with fugacity lambda, say, on G. So I will explain what fugacity means in here later, but let me first write it. This is a random independent set. So distribution of the independent set of G, which is drawn according to the distribution. The probability that I is picked is exactly lambda to the I over P of G of lambda. So this is a probability distribution. For all I, if you add the probability, then this is 1. So in hardcore model, so we pick this, I in the proportional to the, lambda to this size, and you normalize it. That's what's happening here. In hardcore model, we say that we let the occupancy fraction to be alpha of G of lambda, which is 1 over G expected size of I. So expected fraction of the vertices in I is what it is. And one of the reasons why we choose this function is that it's actually, it provides some tool to actually, measure this kind of things. So what's this? The probability that each I is chosen is exactly this. And expectation of size of I is you multiply this and then you add. But what's this? You take this and you take the derivative with respect to lambda, then you get this, minus 1. So this is nothing but lambda times P prime of lambda over PG of lambda, which is lambda over, say, G, and you take the log of this and you take the derivative. So there are some relationship between, average size and this, function. So it provides some, way to actually deal with the, this polynomial and then get some meaningful, conclusion regarding the graph and independent set in there. So why this model? Imagine you have some physical system. So in physics, so there are some atoms, but you have this system, and those atoms are occupying some spaces. And of course, in physical system, atoms cannot occupy two closed spaces. They push each other. So they cannot be too close. So in this space, let's say there are discrete number of spaces, locations that you can have, but the atoms here, then atom cannot be here too, close. Then you can kind of, draw this as a graph, so that if two positions are too close, you add an edge. Otherwise, you don't add an edge. So you have a graph, and the atom can occupy the vertices, which is location, so that there are no edges between. So the position of atom is an independent setting graph. So now, we have this system, and some atoms can come in or some atoms can go out. It depending on the situation that it is more likely to atom to come in or less likely to atoms come out. For example, if you are inside of water, then the pressure is strong, so atoms are trying to get in. But if you are out at the air, then atoms tend to not, get inside of your, wherever you are. Yeah. And that's measured by fugacity. So here you have fugacity. If fugacity is positive, then it's more likely that to pick a larger independent set. So this position of atom changes over time, and it's a probability distribution in some sense. And if fugacity is large, then atoms are trying to come in, so it tends to that there are many atoms. But the fugacity is small, then we tend to choose a smaller independent set. It's more likely to be chosen. Then the atoms are trying to get out. So, and it's very few atoms are coming in, so the number of atoms here are less. So that's what this fugacity is measuring. Anyway, this hardcore model provides a probability distribution on the state of this system, the position of atom, which is a state of this system. So this kind of provides a motivation of studying this, hardcore model. Anyway, so note that if you consider this is nothing but the average size of independent set. So you just, list all the independent set and you take the average size. And now we want to prove the following. So if G is a triangle free graph, with the maximum degree at most D, then maximum degree at most D means that it doesn't have many edges, so it must have a large independent set. Then this average size of independent set divided by n, to be precise, because of this vector. So this is at least log D over D. So in other words, average size of independent set is at least this. So that means there exists at least one average independent set with size this. So this has some application in Ramsey theory, but maybe we do that after we actually prove this theorem. So let's say for positive real number, WG be a number such that WG times e to the WG is G. So this is some definition, technical definition, not important. Later we will use that, but it is not so important. Let's say you consider a random independent set I drawn from the hardcore model. with fugacity lambda. We say that vertex B is occupied if it is in the independent set, and B is uncovered if its neighborhood are, none of them are occupied by the independent set. We are saying this because if you have this and here, if you know this U is in the independent set, you automatically, B is not there. But if none of these are there, then you might, this B might be there and B might not be there. But the probability of B is in the independent set or not, assuming none of here are occupied, that can be somewhat measured from the definition of this hardcore model. So now what do we want to prove? We want to prove that that this average size is at least this. So we want to measure this alpha of G of lambda. But if you see, whether this B is in the independent set or not is not really relevant to whatever happens in here. Whatever vertices in here are in I has a less effect on whether this vertex is in the independent set or not. It's more related to the neighbors. So we will use that, and let's say PB is the probability that the B is in independent set, and QB is the probability that it's uncovered, or its neighbors are not in the independent set. And let U be the set of uncovered vertices. So U is again a random variable. So V is I only occur, V is in U. Only uncovered vertices can be occupied. Moreover, as I mentioned before, here, and you have the rest of the vertices, for each independent set J inside of this G minus the close neighborhood of B. So any independent set here can be corresponded with the J union with B. So J doesn't contain any vertices here, so you can consider this. But in P of G, the term is corresponded is this, and term that's corresponded to here is actually one larger. And then what does this correspond? What does this tell? All the independent sets, so assuming Q is, assuming QB happens. So because in order to P to happen, QB must happen, right? So probability of PB is same as probability of PB and QB. Assuming say QB times probability QB. These two are same. Sorry, this is actually, P was a probability, not the event. PB is, say, QB times probability that B is occupied, assuming B is uncovered. So this. Then what's the probability here? So we consider all independent set J where B is uncovered. Then those independent sets have a two type. Either independent set which doesn't contain B or which does contain B. But we can kind of pair them up. if V is not covered, so none of these are chosen as an independent set, and this is also not chosen, then that's exactly independent set here. And the other type is that the vertices here and vertices here are chosen, but none of them are chosen. It's here. So they can be paired up so that this corresponds to this term and this corresponds to this term. So whatever term here we have for some summation, so for whatever this A is the exactly independent set here, you have this over the term where B is occupied is this summation of J in A lambda times lambda to the J. Let's write it this way. So this is this probability. Out of all instances where B is uncovered, you take the ones which corresponds to the one that B is occupied. Then you just divide this here, then this is nothing but the lambda over 1 plus lambda. So PB is lambda over 1 plus lambda QB. So this is what we know. So now we want to measure this alpha of G lambda in two ways. So for that, let P prime be a vertex of BG chosen uniformly at random, and let Y be the random variable which measures the number of uncovered neighbor of B prime. So then what we get? So first we count this by the normal way. So expected number of, so what was alpha of G? Alpha of G is that the expected size of independent set. Then that's same as that for each vertex, you add the probability that it is in the independent set. So this, and you can use this to rewrite this as a lambda over 1 plus lambda times QB. V is in BG. But watch this. So lambda over 1 plus lambda, and you take it out. V is BG. Then what's QB? QB is the probability that V is uncovered. So we have V, its neighbor. So we want none of these are occupied. But some of the vertices outside might be already have neighbors. Then these vertices are automatically, so these belong to I. This doesn't belong to I. Then, or some of the vertices here might have edge outside. Then, if you consider, these vertices are already, cannot be chosen, cannot be occupied, because its neighbors are already in the, in the independent set. Meaning that these are not uncovered, so these are anyway cannot be in here, but these are uncovered. So this can be chosen as a vertices in I, or can be not chosen. So these are already fixed that none of them are occupied. These are the ones that we have to consider. Whether if none of them is occupied, then B is uncovered. If one of them is occupied, then B is not uncovered. So we want to measure the probability that this is uncovered. So we want to measure the probability that none of them is occupied. So what's the probability? Let's say there are j of them. Then j is between 0 and d. The probability that is actually j of them are occupied. J of them are uncovered. And probability that assuming this, probability that no none of j uncovered vertices are occupied. Now we want to measure this. So we have uncovered vertices. So here this is already covered. So these vertices are not our worry because it's sure that none of them is occupied. So what's the probability that this belong to I? Again, this is uncovered. And what we show is that when it is uncovered, the probability that this is occupied is lambda over 1 plus lambda. So that happens with lambda over 1 plus lambda. So the probability that this is not in here, assuming this is occupied, is 1 over 1 plus lambda. And there are j of them. And because G is triangle free, its neighborhood has no edges here. So these are actually independent set. So even if this one is in the independent set, does not have any effect on the whether this is in independent set or not. So these are, and especially when this is uncovered, that so all of its neighbors are not in I. So this is in there or not are independent events with the probability this. It is not in I with the probability this. So this probability is nothing but 1 over lambda to the j. But what's this? This is y. No, I said it wrong. This is y. This is exactly y. So this is a probability that y has ig, y is g, y is j, and this is 1 plus lambda under 1 to the y. And this is nothing but the random choice. So this is lambda over 1 plus lambda. N is a random choice. This can be converted into the expectation of 1 plus lambda to the minus y. So here, yes. So here two things are at random. You choose this one vertex B prime at random, and you draw this I independent set according to the hardcore model. Then you get this. So what you have, alpha g of lambda is lambda over 1 plus lambda times expectation of 1 plus lambda to the minus y. So we have one way to express this alpha of g. And another way is that as we have above, here these two are same. Summation of b and bg, lambda over 1 plus lambda, qb. And we can actually write this e of g, y, its expectation as 1 over n for all vertices in g. And for all its neighbor, we add the probability that its QB is, this is not covered. Give me a moment. So yeah. So this is expectation is of the vertex. So this is the random choice of vertex. And once you choose the vertex out of neighbors, you add a probability that each of them is uncovered or not. So this is the expected number of uncovered vertices here. So which is expectation of y over the all two random choice. B is random and then I is random. So this is so you can write it this way. This is expectation over B and this is expectation over I. So you fix B, then on B its neighbor, and then I is at random. Each vertex is has the probability QB of being uncovered. So that's what it's here. And because of this, we can rewrite this. So in the following way, D times 1 plus lambda over lambda, alpha G, lambda. Because, so what? So you have this, right? So what's this? For each U, you add, for each B, you add its neighbor. And you add QU. Then for fixed U, how many times does QU add it? Because G has a maximum degree at most D. So QU is added at most D times in here. So this is nothing but 1 over N minus B in VG. Let's just say W in VG. And D times QW. This is the upper bound of this. And you apply this to here, then you get this, which is an upper bound. And this is actually an equality if G is D-regular. But for the graph with maximum degree D, this is an upper bound. Then this provides that alpha of G, lambda, is at least D1 plus lambda over lambda, expectation of Y. So we have this and we have this. But this is a bit difficult to deal with. So what do we know? 1 plus lambda to the minus x is a function looks in this way. This is convex. So convex function, if you choose two vertices and take the function value and take the average, then that's bigger than you average out this number and then take the function value. So you actually have 1 plus lambda minus expectation of y. You have this. So this star and this 2 star. Now we use this to bound. So what do we get? Alpha of G is at least the lambda over T 1 plus lambda maximum of x T 1 plus lambda minus x. Yes, and give me a moment. And we want to so on here as x increase, this increase and this decrease. So we want to find the give me a moment. So you have this 2 So I said it wrong. So you have no control on x. So x, so here, let's say x is the expectation of y. You don't know what it is. But you know that for certain, there is some, so this is some number. We don't know what this number is. For that given number, we have these two inequality. So we choose the worst x so that the maximum of these two are the lowest. Then this is definitely a lower bound. So this is lower bounded by this for some x. But that x could be the worst case. Then you put this. So now we have to optimize this. And when this minimum occurs, when these two are same, because this is x as x increases, this is an increasing function and this is decreasing function. So the maximum of these two are this, and this is maximized when those two are same. Then when does this occur? So when x equal d times 1 plus lambda minus x occurs. And if you take the log, this is nothing but log lambda plus 1 x equal log 1 plus lambda d. And here, from here, what you conclude is that we have this weird definition of W. W of G is the number satisfying this. Then you do some computation, then, it's obviously when this holds, and you get the, say, with this choice of, when this holds, you get the x which makes this true, then you plug this in, then this some equation, which is, it's not too important to actually know what it is. But as we know that this is roughly log g minus log g from the definition here. If you take log g minus log g and log g here, then this you get g over log g, and this becomes log g. So you multiply, then it's close to g. So you use that and plug that in, then alpha of g lambda is at least 1 plus alpha of g and 1 over log d is at least 1 plus 0 of 1 times log d over d. So you get this. So now only one thing to left is that we want to show that the alpha of g1, which we wanted to measure, is actually as large as this alpha of g 1 over log d. So in some sense, we want to show that this is monotone increasing in terms of lambda. So that's all remains to show. I think I didn't exactly measure the time, but it's a bit over, but let's keep doing it anyway. So we know that this is the definition of the independence polynomial. And what happens if you take the derivative twice? Then you have a size of I times size of I minus 1 times lambda to the I minus 2 I. So you multiply lambda 2 here, lambda 2 here. Then this is nothing but the expectation of I times I minus 1 in this hardcore model. this is same as lambda square p double derivative, second derivative of lambda. So by using this, what we know is that if you have this expression, let's just write p as a p of g of lambda. And if you write this, then this is nothing but the expectation of I times I minus 1 plus I. Sorry, this is p of g lambda. You have to divide it because when you choose it at random, the probability is this. So here, that's exactly this, right? And by the, as we've seen before, first derivative divided by p is this. So this is nothing but the expectation of I square in this hardcore model. Now we want to show that this is monotone increasing. So we want to show that its derivative is positive. If you take the derivative of this alpha, which is lambda p prime over p, just basic probability, basic calculus shows that computation you can do it yourself, so not so important. And from here, you use this here, then this is nothing but the 1 over lambda, expectation of I square minus expectation of I square, which is variation of size of I over lambda, which is non-negative. This shows that alpha 1 is at least alpha g 1 over log d. This concludes the theorem. So, as a corollary, this actually yields a bound on Ramsey number, but it's a bit over time, so I will stop it here. And next lecture, we briefly see how this implies Ramsey number 3, or lower, or an upper bound on Ramsey number 3k. And we use a similar proof with a more complicated analysis. We can actually count the number of independent sets in G and find the upper bound. So that's what we will do next time.